Cool. Take it away, Collins.
Sweet. Can you all see my screen?
Yes.
Yes.
Awesome. Okay, so I'm Collins Huff, work at Palo Alto Networks. I'm going to be talking to you about a project I've been working on to quickly send and receive networking packets on Linux using Rust. The broad strokes overview for this talk, I'll talk about the features in Linux that allow us to do this, finding a library for AFXDP in Rust, rewriting components of it to meet my needs, debugging performance issues, and writing FFI bindings so that we can call our Rust code from C. But before I get into that, I'll give a little bit of motivation for why I care about this. If I can advance the slide. Too many. So yeah, I'm interested in scanning the internet. And by that, I mean finding all hosts on the internet with a certain port open, running a certain service, vulnerable to a certain exploit, those types of things. So for any of those types of tasks, we first need to find open ports on hosts on the internet. What do I mean by open ports? To start at the very basics, if you want to run a service on the internet that other people on the internet can connect to as clients, you need a couple things. You need an IP address, which uniquely identifies your machine on the internet. You need a port, which identifies the service on your machine, and you need some sort of protocol to talk to one another. I'm going to be talking about finding open TCP ports, but the same principles apply for UDP. I'm just not going to get into those details. So TCP, it's a reliable protocol for transmitting data between two hosts on the internet. So if you send a packet from one host to another using TCP, you can be assured that it'll actually arrive at the other host. The way it does this is by using acknowledgements of data received. So when you send some data, you keep track of the data that you've sent. When the other host receives the data, it sends an acknowledgement of that data. And if you don't receive an acknowledgement for the data that you sent, then you resend it. So when you first set up a TCP connection, you complete what's called a three-way handshake, which consists of 3 packets. The client first sends a SYN, the server sends a SYN-ACK, and then the client sends an ACK. So pictorially, this is what that looks like. SYN, SYN-ACK, ACK, and then the client and the server can exchange data using the reliable mechanism that I described previously. So the tool of choice for scanning for open TCP ports, for me at least, is ZMAP. There's another tool called MassScan, which operates similarly, but in short, what it does is it sends TCP SYN packets to hosts and listens for SYN-ACKs. And if it receives a SYN-ACK in response to a SYN, then it knows there's an open TCP port. When you are scanning the internet, the speed at which you're scanning is important. So there are over 4 billion IPv4 addresses. Scanning all of them at a rate of 100,000 packets per second takes 12 hours. Scanning at a rate of 10 million packets per second takes 7 minutes. So because speed matters, we should consider the mechanism by which we are sending and receiving packets. So usually when you send and receive packets, the way you do that is you have some user space application, and it makes a couple different system calls to the kernel in order to send and receive packets. So if you're a client, you make a socket system call, and then a connect system call to create that TCP connection, and then a send system call to send data, and a receive system call to receive data. And when you're making those system calls, what's happening is you're telling the kernel to do some stuff with your networking hardware and also maintain state for your TCP connection. So yeah, one of the nice things about this is that you as the user space application do not need to know what networking hardware you're running. The downside is, for our purposes, we want to scan really fast. We don't need the extra overhead that the kernel incurs by keeping state for each TCP connection. We just want to send SYNs as fast as we can and receive them as fast as we can. So we need to look into some other methods. So other methods for doing this, there's another address family you can use in Linux called AF packet. Basically just a different parameter when you make your socket system call. And what this does is it gives your user space application access to raw Ethernet frames. And it avoids the overhead of the TCP IP stack in the kernel, but it still has some overhead, namely each time that you want to send a packet, you have to make a system call, and that system call copies the packet data from user space into the kernel, where it's then sent on your networking hardware. Another option is to use techniques like kernel bypass. So these completely bypass the entire Linux kernel networking stack. They're obviously super fast because you don't have any of that overhead, but they're generally a bit more difficult to use because you have to load a kernel module. And also in the case of PF ring, you have to buy a license. And yeah, so ZMap by default uses AF packet, that somewhat slower method that I described first. Optionally, it'll use PF ring. You have to have a license for it, and the license costs $150 per network interface that you want to scan from. And I'm too cheap for that. So I started looking into other ways of sending and receiving packets. And the way that I found is this feature called AF XDP. So it's a third way for fast path packet processing. It's in the kernel, nearly as fast as kernel bypass, not quite as fast, built in so you don't have to load a kernel module, a lot more performant than AF packet. So you can see here, we're able to send 21.79 million 64-byte packets per second compared to 1.24 million using AF packet. So to step back a little bit, we're talking about a bunch of different features in the Linux kernel. Might be useful to have an analogy. Imagine that you're going to the airport. You are the packet in this scenario, and all the stuff in the airport is your networking hardware and Linux operating system and so forth. So imagine you're going to the airport. In-kernel packet processing with AF packet is like showing up at the airport, checking in, going through TSA, showing up at the gate, and then getting on your plane. Kernel bypass is like parking your car at the airport, walking onto the tarmac, and getting on a private jet. And AFXDP is something like going through TSA pre-check. So faster than everything in the existing in-kernel with AF packet, not quite as fast as kernel bypass, but we'll take it. This is a diagram of how AFXDP works, and I also will show a little bit more about the Linux kernel networking stack. You can see here, you've got your networking hardware at the bottom, your kernel here in the middle, and your user space applications up at the top. So when you are using AF packet, you go into the Linux kernel networking stack through the traffic control system, build a socket buffer. This is where that copy and potentially memory allocation overhead comes, and then it goes out the networking hardware. Whereas with XDP, packets come in on from the networking hardware, go to XDP, and then go straight to your user space application. And it's not shown here, but you can imagine kernel bypass is like going directly from user space to the networking hardware along this path. So in order to use AFXDP, you need to set up a couple different data structures that are shared between the kernel and your user space application. You need two queues for the transmit path, two queues for the receive path, and then a big block of memory called the UMEM region, which is where you will actually write packet data and read packet data that come in on the network interface. So I'll talk a little bit more about the UMEM region because it's relevant to the Rust specific stuff I'll talk about in a moment. The UMEM region, like I said previously, it's a big block of memory shared between user space and the kernel. We need to allocate this big block of memory somehow. So maybe we allocate it on the stack. Not necessarily a great idea because this could be a huge block of memory. Maybe it's hundreds of megs, maybe it's a gig. And you don't want to allocate that on the stack because it probably just won't work. You'll probably blow the stack and your program will crash. The other option is to allocate it on the heap. Also not a great option because if you allocate this big region of memory on the heap, it can slow down your allocator by causing fragmentation. So it makes it more difficult for your allocator to find regions of memory to use for other purposes. So the alternative to those two is to allocate it with something called mmap. Mmap typically is used to map a file into memory so that you can operate on the contents of that file as if it were addresses in memory. However, there's another way you can use mmap, which is called using the mmap anonymous flag, which means it's not backed by any underlying file on the file system. It's just a big block of memory for your program to do whatever it wants with. So we're going to use mmap to allocate the UMEM region. So pictorially, what I just described looks like this. These are the data structures that we need to set up in order to use AFXDP. You've got the UMEM region, big block of memory allocated with mmap. It's divided up into frames or frame descriptors. This is where you'll actually write packet data and read packet data. When you want to transmit a packet using AFXDP, what you do is you write the data that you want to send to one of these frames, and then you take the frame address, which is just an offset into the UMEM region, and you put it on the transmit queue. The kernel will pick up the frame address off of the transmit queue, read from the UMEM region, and send that packet using the networking hardware. Once it's done that, it'll take that frame address and put it onto the completion queue. And your user space application reads from the completion queue, reads those frame addresses that have been transmitted, so it knows what frames can be used again to transmit new data. The receive path, the way it operates is you put frame addresses onto the fill queue, and this tells the kernel that these frame addresses that are on the fill queue can be used to receive data that come in via your networking hardware. When a packet comes in, the kernel will write the packet that comes in on the networking hardware to one of the frames that is in the fill queue, and then it will put that frame address onto the receive queue, which your user space application will read from. Once it receives a frame address, it will read the corresponding packet data and do whatever it wants with it, parse it, process it, ignore it, whatever. So that's probably a lot of background. I'll stop here right now for questions, and then we'll get into the Rust stuff. Questions?
Maybe a dumb question, but for your frame allocations, do you know what your frame size is ahead of time? Like, is there a fixed one for the snack packet, or is that like frame, like packet size plus some overhead.
Yeah, so when you create the UMem region, you first create it with mmap, and then you do a system call to like register this region of memory with the kernel. And when you make that system call, you also specify the max or the frame size. So that's the max amount of data that the kernel can possibly write into a frame. Does that answer your question?
I was just more curious as to like how one computed the frame size in this context.
You can set it ahead of time. You could set it based on whether you expect to receive jumbo frames or not. Or you can just set it to the default, which I don't know. I don't remember what it is off the top of my head. It's around like 2048 bytes.
Cool. Thank you.
Sure thing. Saw something in the chat. Why use Linux altogether? Couldn't you get faster without a kernel and a queue? Yeah, that's a good question. You could definitely do that. I don't know how to do that. Do you know how to do that? That seems awesome.
There was another question in the chat from Johan.
How do you know the size of the frame that got onto the RxQ? Okay, that's a good question. Also, the data that's received on the RxQ is actually frame addresses and the length of the corresponding packet received. So it's actually three things, and then some optional flags. But those are the two main things you receive from the RxQ. It's the address and the length of the data received. So that's how you know the frame here acts like a buffer. Yes, it's like a buffer that you use to send and receive packets. Other questions before we move on? Okay. So when I started out, I found this library, XSKRS, which use libbpfsys, some bindings to system calls to set up these data structures. The examples indicated to me this is a reasonably straightforward translation of the C code that is in the kernel source tree under the AFXDP example, translating that into Rust. And this was super awesome to find. It was a great starting point for me to get my bearings with all of these different data structures and how to use them and the system calls. So kudos to this guy for writing it. It was also very well documented. But it didn't quite work for my use case. The first is a design problem that I'll talk about that didn't allow me to send and receive from multiple threads, which we need to do in order to use this with ZMap. So the way ZMap works more specifically is it has one thread that sends packets, SYN packets, and one thread that receives SYNAC packets. Also, it didn't really provide a clean API to use this from. You had to manage all of these data structures, like which frames are on the TX queue and RX queue and completion queue and fill queue yourself. And so that would make it difficult to write a C foreign function interface for this library. So we'll tackle the first problem. The original design shown here, you have this UMem struct, which contains the underlying mmap area, the region of memory that we allocate for the frames. And then when you want to read from the UMem and the underlying mmap area, you pass in an address and a length that you want to read. And when you want to write, you pass in a frame descriptor address and the data. So pictorially, what this looks like is you have a UMem struct. It owns the underlying mmap region. and it takes as references the frame descriptors and the data that you want to write, or the frame descriptor that you want to read from. So the reason that this design doesn't work for sending and receiving from multiple threads, I'll explain that with an analogy. So imagine that you tried to manipulate two disjoint regions of vector with the following, from two different threads with the following method. Imagine that you took that vector, you took the indices of that vector that you want to manipulate in thread 1, create a range out of that. The indices that you want to manipulate in thread 2, create a range out of that, pass those two ranges to your two threads, and then you try to pass a mutable reference of that vector to each thread. That's not going to work because in Rust, you can't have two mutable references to the same underlying data. However, conceptually, this should work. And Rust, in fact, does provide a method on vectors to do exactly this, where you can create two mutable slices from disjoint ranges of indices. So you could pass those to the two threads and operate on them independently. So we need to do something similar here with our frame descriptors and our memory. So what we want is something like this, where the frame descriptors either own or have references to the underlying memory corresponding to that frame descriptor address. So unfortunately, or I guess not unfortunately, but just a fact of life, I had to use unsafe features in order to implement this. The reason being, there's not really an existing safe API on top of mmap in the Rust standard library. And when you create the mmap region in Rust, you make a system call, and that system call returns a raw C pointer to your user space program. And then you have to take that raw C pointer and construct a slice for each of these frames. And the only way to do that is slice from raw parts mute, which takes the address and the length, and then creates a slice from the underlying memory, a mutable slice from the underlying memory. So what we do is we iterate over the frames using the starting address of our mmap region and the length of our frame, and we construct a mutable slice corresponding to the mmap area for that frame address. And now what this allows us to do with this new revised design is we can split up the frame descriptors, the frames, into two disjoint sets, two disjoint slices of frames. And we can pass those to two different threads. So we could pass one range of frames to one thread and use it for the transmit path. And we can pass another range of frames to another thread and use that for the receive path. And this is what that looks like in code. So each frame has a arc mmap area, and then constructs the mutable slice of that data using the memrange mute call. Or sorry, the slice from raw parts. Memrange mute is a wrapper on top of that. So now we've done that. We have a simple API. We have two structs, a transmit struct and a receive struct. The transmit struct has the frames that we want to use for transmitting, the transmit queue and the completion queue, and the receive struct has the frames that we want to use for receiving, the receive queue, and the fill queue. And when you send and receive, these calls maintain all of the bookkeeping needed to know which frames are good to use for transmitting, which are not good. It updates the frames that can be used for transmitting and receiving, and does all of the bookkeeping of those structures that we looked at earlier. So any questions about this? Can you send, do you mean 9,000 length octet packets?
Jumbo frames.
Jumbo frames.
Yeah.
I have not tried to send and receive jumbo frames. I didn't need that for my use case. I would assume so. The only caveat, I believe the frame, the length of each frame has to be a power of 2. I think that's right.
Yeah.
So you could, that's the only restriction I know of. So I don't see any reason why you couldn't send and receive jumbo frames.
Sorry, go ahead.
No, you go ahead.
So XSK right here, that handles all of the hard parts with the data structure and the UMEM and stuff. You just send and receive with this?
No, that's more of just a container for the two transmit, the transmit struct and the receive struct. So when you call create a new AFXDP socket, it returns it as a struct that contains these two structs. What's actually doing the bookkeeping is the transmit struct and the receive struct. Actually, there's a typo here. This should be xsk.rx.receive. Sorry about that.
Got it. Thanks.
And what is it you're actually doing with all this stuff as you get it? And when you receive the packets, are you using it to look at them, or?
Yeah, the whole reason for doing all of this is what I covered in the very beginning, which is using it to send and receive packets with ZMAP, which is a scanner to scan the internet. So we're trying to scan quickly. So yeah, when we're using the TX path, just for my use case, what you're sending are TCP SYN packets, and what you're receiving are TCP SYNAC packets. And you're looking at those SYNACs, you're parsing them to get the IP address and make sure it corresponds to a in total UMEM. Okay. Okay. I honestly haven't tried to send and receive jumbo frames, but I can look into that. Actually, now that you mentioned it, I do remember seeing that the system call for registering the UMEM region would fail if you tried to allocate more than a certain amount. But I'm sorry, I don't have more a clear answer on whether this can handle jumbo frames. Good to move on. Okay. So now we've got our simplified design that we can use from ZMAP. The whole point of this is to scan quickly, so we need to do some performance analysis. The way I did that is with a setup that looks like this. We have one server transmitting UDP packets, and it transmits UDP packets with payloads 1 through N. And then a receive server receives packets, parses those UDP packets received, and verifies that the payloads 1 through n were in fact received. So make sure that we're not dropping packets. You can find that here. If you want more detail on how I set up this performance test, I'll link to kind of like a blog post on this. The short of it is I used Equinix Metal, which is a service, pretends to be like a cloud service, but it gives you access to bare metal servers that you can configure, and they have 10 gig Ethernet NICs that you can use to test this. But yeah, that's the setup. So when I ran this, it was too slow. If you do the math on a 10 gig Ethernet link sending just TCP SYN packets, you should be able to get about 14 million packets per second. And this is only getting 5 million packets per second. So you can see that on the bottom here, there's just a straightforward calculation using the duration of the scan or the duration of the test and the total number of packets sent. So we were only, actually in this case, this test we were getting 6 million, but between 5 and 6 million. So this was too slow. So we need to figure that out because the whole point is to scan quickly. So the method I used for figuring this out is using something called flame graphs. It's a tool that allows you to visualize where your program is spending time. And the way it does this is by stopping your program at a certain interval, seeing what function is currently being called, and keeping track of what being functions are being called during the execution of your program. And the way it visualizes this data is by this nice red and yellow picture here. So the x-axis, or the width of each block, represents how much time was spent in this, or how much time this function was a parent of where your program was spending time. And the y-axis represents depth in the call stack. So in this way, you can visualize where your program is spending time. And this is the flame graph for the library when it was only transmitting between 5 and 6 million packets per second. And we see that it's spending a ton of time in this TXQ wake up method. And so we can track that down. Why are there yeah, that's a good question. Panic catch on one. I'm not exactly sure what that is. Does anyone
like unwrap or something? Maybe, I don't know.
Yeah.
Yeah. Did you compile this with the panic stuff enabled in Rust, or?
Yeah. I didn't disable any of that.
Yes, that's probably a runtime, right?
Yeah, that would make sense. But panic in the call stack. Yeah, that's a great band name. I'm gonna go register that domain right after this. Anyway, what we're looking at is the TXQ wake up. It's spending a ton of time in this, and we're not really sure why that is. So there's one more thing I need to say about AFXDP. I talked about how to send packets. You write frame addresses, you write data to frames, put the frame addresses on the TXQ. There's one more step you need. You only need this for certain networking hardware, but the networking hardware I'm using, or driver I'm using, is Mellanox MLX4s, which require this, which is you have to wake up the kernel at certain intervals in order to continue processing packets. So that's what this is. And the gist of what the performance issue is here is just me not knowing how to use these features properly, which is I'm calling in the send method complete frames and put batch on TX queue. Complete frames reads from the completion queue and updates the frames so that you can use more frames to transmit packets. And put batch on TX queue takes whatever is in your batch size and puts it on the TX queue. And actually, if you look into both of these functions wake up the kernel. So when you put a batch on the TX queue, you call produce and wake up. And when you call complete frames, I saw this somewhere and I thought it was a good idea, which is if there are no frames received on the completion queue, then wake up the kernel. This was a mistake. So you really only need to wake up the kernel once per send call. So basically, the answer to our performance issues was just commenting out this extra wake up in the complete frames method. And once we do that, you can see, is this too small? I can zoom in on this and show you what's going on here. We're getting the 14 million packets per second that we wanted. So that's an example of using flame graphs to debug a performance issue. Questions on that? Yeah, and then this is the new flame graph. The wake up call is completely evaporated. That's not on here because we got rid of it. We're only calling wake up. I think somewhere in this stack when we actually put a batch of packets onto the transmit queue. Cool. So now that we have done that, we have a new problem. We've sped up the transmit path, but the receive path can't keep up. So if you'll see here, this is actually just the output from the previous run. We're sending at 14 million packets per second. But let me see if I can zoom in on this. Using that technique I described earlier in the performance testing setup, where we parse each packet and look at the UDP payload and make sure that every packet we expect to receive, we do in fact receive, we see that we are missing 7.8 million packets out of 10 million. So 78% when we're running at 14 million packets per second, which is bad. Honestly, this probably would have worked for my use case, but I didn't want to leave it at this. The reason being, if you're transmitting at 10 million packets per second, say, with ZMAP, even the most common services, you're only going to get a hit rate of like 1.5% for port 443. And so it probably would have kept up, but I just wanted to see if I could figure out what was going on here. And so what I determined using a combination of flame graphs and just knowledge from previous work is that the way that I'm doing receiving and parsing is suboptimal because we're copying data multiple times. So this is the receive function initially. It takes a mutable slice of bytes to put packets into. When it receives a packet, reads it in the UMEM region, it copies it out of the UMEM region into the packet receiver, and then it returns the size of the packet that was received. So we've got an additional copy. And so what that looks like in terms of diagram, the packet data exists in our XDP library. It exists in the UMEM region, specifically in one of the frames in the UMEM region. The initial way I was doing it was every time that a library user would call receive. It would copy the packet data out of the library into the user of the library, into that packet receiver. And then it would call some user-defined parser on that packet data after it was copied. This is suboptimal because we have an additional copy. When you're trying to receive millions of packets per second, copies are very costly. It's a very costly operation to do millions of times per second, because you potentially have to read whatever the max frame size is of bytes and move it into an entirely new memory location. But conceptually, we should just be able to call our user parser on the packet data in place. There are a couple of different ways we could do this. We could figure out some way of returning a reference to the packet, but then we need to, or we could even pass ownership of the packet data to the library user. But then that adds complexity to the library user, as we have to manage the ownership of the frames and remember to return ownership of the frames back to the library once we've done whatever we want in terms of parsing with them. So the other option which I used is use a closure. So our library accepts a user-defined function that operates on the packet data in place and does whatever it wants with it. So what that looks like in terms of diagram is the packet data exists in the XDP library. The library user writes some parser and then registers that with the library, or passes that into the library as a closure. So what it looks like here is we have a new function, receive apply, takes in F, where F is a FN mute that operates on a reference to or on a slice of bytes. And when we call that, or when we receive a packet, we get our data, and we call our function on it. And so once we've done that, we go from missing 78% of packets to 4% of packets in an experiment of sending 10 million packets at 14 million packets per second. So this is better. This is still not quite ideal, but this is where I left it. There are some options for how we could optimize this further. One is we could make our parser more efficient, maybe using vector instructions or something fancy like that. I don't know exactly how you would do that, but you try to make the parser more efficient. You could try to scale out the parser, so multi-thread the parser. And to do that would require what I was describing previously, where like the XDP library would pass ownership of frames back to the caller of the library, and then they could put those on queues and parse them using multiple threads. Another option is a little bit more in the weeds, but network interfaces generally have multiple queues that you can use to send and receive from, and you can register a separate, or you can create a separate XDP socket on each one of those queues, and then you can call you can use ethtool to hash the 5 tuple of or the 4 tuple, the source IP, source port, destination IP, destination port of packets received, and round robin them to the different queues. That's another option. That's in the weeds, so I won't get into that. But yeah, that's what I was working on with optimizing the receive path. Questions? Okay, moving on. The final step for what I'm trying to use this for is we need to write C FFI bindings, so we can call our Rust code from C. The reason being ZMap is written in C. Doing that was actually reasonably straightforward. Just follow the steps in the Rust FFI omnibus, which tells you how to do this. What it looks like is this XSK new function wraps our existing Rust library. All of these functions exist in a separate crate, which is XTPSoc FFI. The general convention for writing bindings is if you are wrapping an existing C API in Rust, then you put a sys suffix on your crate, SYS suffix on your crate. If you are writing FFI bindings for existing Rust code to be called from C, you put a FFI suffix on it. And what that looks like I said previously, this XSK new function wraps our existing Rust library. It has this extern C keyword and the no mangle macro. And what this does is it tells the compiler not to basically generate a symbol for this function that can be called from C. So the no mangle macro makes it so that the compiler won't change the name of this symbol to something else, which it does for reasons when you don't use this. The main one I can think of being if your function is generic and you're using static dispatch, it creates a new actual symbol for each instantiation of that function for whatever over your generic type. That's in the weeds. But yeah, this creates our XSK struct, turns it into a pointer, and then returns it. When we call send, it takes in the XSK pointer, asserts it's not null, does the type conversion, and then constructs a slice from the packet data, which is passed in as a pointer and a length, and sends it. Similar idea for C, we pass in the packet receiver, construct the pointer, slice from raw parts of the packet receiver using the pointer and the length, and then receive into that and return the length of the received packet. And this is a more complete example of how to use this from C. And if you want to see what this looks like in ZMap, you can go here, which is my fork of ZMap using these features. That's all. Questions? Is that packet loss %? Yeah, it's somewhat random. It depends on, I guess, a couple different things, like what other background processes are running. Maybe some like traffic shaping of the networking hardware between your send and receive server, but from what I've seen, between 4 and 8% of packet loss. Obviously not ideal, but we have some ideas of how to fix that. Did you? Yes, I did use the release flag in the benchmarks. They say most humans only use 10% of their CPU, whereas Einstein used 20% of his CPU. What would it look like if we used 100%? That's a great question.
Sorry, that was a really dumb. It's like using the release flag, right? It's like, yeah, sorry.
Yeah, that's like whatever the mind expanding meme.
I was curious. So how many like threads total then does a process running the scan use? Like, it seems like there's only a handful of threads, or is ZMap like doing this a bunch of different threads? Or do you end up doing multiple processes, or you're just using something that you really only have a core or two on the machine that you would be doing this on.
So ZMap by default uses one thread for sending, one thread for receiving, and one thread that monitors statistics about the ongoing scan and prints them out to the console or writes them to a file. It can be used to send from multiple threads, so you can scale up in that way. But I haven't implemented that in the FFI bindings. What that would require is that you, at least with my library, there's a couple different ways you could do it. One way you could do it is what I described previously for optimizing the receive path, where the network interface has multiple queues that it can send and receive from, and you can create a new XDP socket on each of those queues. So you could use that to scale out the sending. But a benchmark I was showing was using a single sending thread, and it was maxing out the theoretical limits for 10 gig Ethernet. But yeah, if you wanted to scan at 40 gigs or 100 gigs, then
I guess then you could, to some extent, maybe that doesn't even make sense, because then the network hardware, right? Like you could, right. You already have some bottleneck on your device. I mean, would you be? I would assume that if you can just double what you're doing by having a couple extra cores and just run multiple processes, that would already be a strategy.
You mean not using XDP, using AF packet, or using XDP with multiple threads?
Maybe I don't know what I mean. I guess I'm just curious to know, yeah, like what resources in the like typical server that you would run this on, what resources are fully saturated?
Sorry, I think I kind of understood. It seems like you could use multi-processing, and ZMap takes like sharding command line flags. So if you have like a lot of cores, I think you could use XDP and just like spin up multiple processes of ZMap, right?
Yeah, you could do that, or you can also do what I was describing previously with the queues. But to answer your question, Scott, about what resources are being fully consumed, I mean, it'll depend on what or how many cores your server has. But at the minimum, you're basically pinning, or not pinning. That's not a good word. That's overloaded. You're fully using 3 cores during a scan, and memory usage isn't particularly high. You're not allocating a ton of memory for the UMEM region, less than a gig. But your networking, your NIC is, if you're scanning at full speed, then it's fully saturated. And if you were try to, actually no. This is one thing I didn't mention. When you create an XDP socket on a NIC and on a queue, it completely takes it over, and it can't be used for other purposes. So yeah, your networking on that interface is completely consumed. Does that answer your question?
Yeah, exactly. Yeah, you can't just. Yeah, the networking. I'm going to stop trying to re-explain it. That answered my question.
Cool.
I mean, you could scale out multiple servers using ZMap sharding to like scan the same range on the same port. So you could just spin up multiple servers, even if in each one would just, right?
Yeah.
But then you might be saturating or using all the resources in your wallet. Then we already went down this project because Collins thought $150 was too steep for a license for that other library. So
yeah, that's true. The goal of this was resource efficiency, and also just I don't know, I find this fun. Other questions?
Could you use the same technique for malicious purposes, like DDoSing a client?
Oh yeah, of course.
So specifically, like, does anything special happen if you just send that initial SYN packet? Would that make the responding user extra vulnerable, or how does that work?
You could potentially, yeah. There's some stuff you could do with like sending many TCP SYN packets from spoofed IPs to try and like exhaust the resources on the target. But in terms of vulnerabilities, not really. It's more useful for finding vulnerabilities. Also on the resource exhaustion, I think the kernel has some features that make that more difficult. Another thing you could do would be use this to do something like a UDP amplification attack, where you find some like NTP server with certain configuration and send a bunch of UDP packets to that server. If it has certain features enabled, it will respond to your UDP packets with a packet that's larger than what you sent. So you can amplify the traffic. And then what you do is you spoof the source, spoof the source to your target, whoever you're trying to DOS, and use that as a means of doing nefarious things. Did that answer your question, or not really?
Yeah, I think so. Yeah.
Another thing is just scanning the internet is by its nature dual use. We scan the internet in order to tell companies about where they might be vulnerable. Attackers scan the internet in order to find servers to exploit. So that's something else to consider. Most IDC would filter out spoofed headers. Yeah, that's also true. What is that called? Where your the network that your some networking device ensures that the source packet or the source IP for packets that you're sending is actually within the subnet that it knows about. Does anyone know what the name of that is? I'm blanking on it.
You're talking about reverse path forwarding?
I don't know if that's the name for it. I'm responding to the question in chat about filtering out spoofed headers.
Yeah.
It might be reverse path forwarding. I'm not sure, to be honest. Let's use EB tables to drop any packets that have incorrect IP MAC port mapping. Okay. Other questions?
Sorry if I missed this earlier, but did you say how long it takes to scan the internet with this?
Yeah, you could scan it in under 5 minutes at 14 million packets per second.
Like all ports or one port?
One port, sorry. All of IPv4. Obviously, when you include IPv6, that's a whole different story. And even at obscenely fast rates, it would take longer than the duration of the universe or something. I don't know what the exact number is, but IPv4, one port, under 5 minutes.
Awesome.
For the IPs that weren't returning packets, or at least you weren't having success getting responses for? Were they all in like certain designated blocks, or was there was it kind of a random distribution of IPs as far as one could tell?
You're talking about when you scan the internet, where?
Yeah, where the black holes are, at least in this case.
Well, first of all, when you scan the internet, you don't use the reserved ranges used for lands. So that eliminates some number of these, this 4 million, 4 and some million. I don't know exactly how to answer your question. I don't know off the top of my head what the distribution is like in terms of, like, if you were to split up all of IPv4 into like /24s, like how sparse or not would that be? That's a good question. I don't know off the top of my head. Is that what you're getting at?
Yep.
Yeah, sorry, I don't have a better answer for that. Other questions?
You mentioned in the beginning that you wanted to scan in order to figure out what services were running. So I assume you do some kind of investigation of the packets that you get back in the response. Are you?
So ZMAP has two sort of operating modes. Well, there's actually more, but the way I use it is use the TCP SYN scan module in order to just find open ports, and then use another program to actually do some application-specific exchange of data in order to determine the service running on that open port. With UDP, you can have ZMAP send UDP payloads, and then if the corresponding UDP service is running on that port, it'll return data that you can then parse to determine if a certain service is running.
Oh, okay, yeah, that makes sense. Thanks.
I have a question. Have you explored using Go? Because it's most, I don't know both of them, so just from a novice user. I thought Go is more used toward networking, and this is more like a networking application.
Yeah, the issue you might run into with using Go for this type of work is it's sort of real time, in that you have to respond to incoming packets in a deterministic amount of time, and Go is a GC language, so you might run into performance issues with GC pauses as a result of that. Although there is this project that does something similar. It's a framework written in Go using DPDK, which was one of the kernel bypass technologies I mentioned earlier. And it also supports AFXDP, cool. But I believe this project, I think it modified something. Yeah, it has a built-in scheduler, so it has to do some special things with Go in order to make it work for that use case. But you should try it. That would be awesome to see how it would perform. Does that answer your question about that?
Yes, it did. Yeah, thank you.
Does anyone else have comments on Rust versus Go for networking stuff?
One more question. What are your the challenges that that you face the most? Is it memory usage? Is it response from the end stations? What's the biggest problem that you faced, and you think it's the biggest challenge in this application?
In terms of writing it in Rust, or in terms of just scanning the internet, or both? I guess I'll take both. In terms of writing it in Rust, like the challenges I mentioned about getting the ownership to work for the use case. Also, there's a whole thing I didn't go into that could be a whole nother talk, which is debugging with a debugger. When you have to cross boundaries from Rust to C, that can get somewhat challenging. And we have to do that because we're interfacing with ZMap. Also, ZMap is calling our Rust code, and then our Rust code is also calling C code in order to do the system calls to set up the structures. That debugging issues from the Rust code to the C code was challenging. In terms of scanning the internet, finding a place to scan, dealing with abuse complaints. So network operators sometimes don't take too kindly to you sending SYN packets, even though it's we're doing it for benign purposes. They don't necessarily know that. They think maybe they're getting scanned by some attacker or something like that, and so they sometimes send abuse complaints to your provider. Let's see. Other problems are just like weirdness of the internet. There's all kinds of middle boxes that do interesting things. So there are some networking hardware that will respond to a SYN with a SYN-ACK regardless of whether there's actually a service running on that port. Stuff like that. Does that answer your question?
Yes, you did. Thank you very much. One more question and I will stop. So I think there is also another Unix utility, Nmap. Does it compare to ZMap or no?
Yeah, so ZMap and Mascan, the two projects I talked about a little bit, they were sort of written in response to performance issues with Nmap in terms of quickly scanning, doing just TCP SYN scans to get open ports. They were designed from the beginning just for that use case, and so they use like the faster packet processing utilities I talked about. If you use Nmap with just a SYN scan flag, it operates similarly to ZMap by default in terms of it uses AF packet to transmit, assuming you're on Linux. But there are still other performance issues, even when you're just doing SYN scans with Nmap. Also, Nmap just has way more features than ZMap. ZMap is just for doing open port scans, or typically used in that way. Whereas Nmap has this scripting language built in that allows you to do the full application layer exchange and match on that and try to find vulnerabilities and stuff like that. So it's got more features, but not quite as performant for just finding open ports compared to ZMap and Masking.
Thank you very much for the explanation. Appreciate it. Thank you.
Sure thing. Yeah, and I guess there's a caveat that's ZMap and Masking both also are sort of encroaching on Nmap territory in terms of they have some application layer exchange capabilities, but obviously not as full-featured as Nmap with its built-in scripting language and huge library of Nmap scripts that you can run.